Today's lecture is continuation for chapter 4, isolated footings. Just a quick summary. We started with chapter 1, types of foundations. We studied the difference between shallow and deep foundations. Then in chapter 2 we concentrated on shallow foundations and we gave an introduction to all types of shallow foundation. Then we left foundations for a while and started with studying bearing capacity and settlement of shallow foundation, how we are going to design shallow foundations based on the bearing capacity and settlement criteria. Then in chapter 4 we studied one type, the first important type of shallow foundations, which is isolated footing. What is isolated footing? Isolated footing is a shallow foundation where I have for each column one footing, or for each footing one column. And we studied how can we design this type for a case of normal force. Then we reached after going to the final details of the isolated footings, how the reinforcement is placed, thickness, plain concrete, reinforced concrete, everything. Then we said that we are going to study a case where we have normal force plus moment. And we said that normal force plus moment, for normal force plus moment we have two cases. The first case, the moment is fixed, it does not change in direction, like the moment of a frame leg. This is a frame and this is the leg of the frame. It is always in this place. It will never change because it is the moment due to loading, and loading is always coming vertical on this frame. Resulting from this vertical loading on the frame, I will have moment at this place here and at this place here at both footings. So I can design a footing based on a moment with a fixed direction. But suppose for this frame I added another load, which is wind load or earthquake load. Wind load or earthquake load, it can come from any direction. So it is not fixed. One time the moment may be, this triangle may be in this direction, other time it will be in the opposite direction. So in this case I cannot depend on a specific direction. I have to choose something in the middle, which is the original place of the column, and say that based on this original place, moment would come from any direction. But in my case here, with a fixed moment, I know that for this column I have a direction for the moment. And we said that the best thing and the most economic thing to design the foundation of this column with a fixed moment is to make something to delete this moment. How can I delete or cancel this moment? Add another moment in the opposite direction. If I have moment in one direction, it is fixed. I add another moment in the opposite direction, the resultant will be 0. So how can I do this? I just shift the column. If I shift the column from the CG outward, then I am adding a moment. We said an example for this. If you are standing on a wooden raft in water, and of course you will be standing in the middle, like the column standing in the middle of the footing. If you decide to move a little bit from the center of this raft and go to the one of the corners or one of the edges, in this case you're going to fall. Simply. Why? Because you will induce moment on this raft. So we want to induce moment on the footing, but in the opposite direction of the fixed moment that is already on the footing. So the resultant will be 0. But what will end up with this case? I have no moment, but the column is shifted. This is the only difference between this footing and the normal isolated footing, because to cancel the moment I shifted the column. So in this case it will not be just a typical isolated footing. It's a typical but with a shifted column. This is the only difference. What was the effect of shifting the column? The effect will be on the cantilevers of the because if I shift the column, then the cantilever from one direction of the footing will be bigger than the other direction. So in this case the moment will be more, and I have to study this moment, and I have to study the moment on the footing in the other direction. It's not the moment acting on the footing, it's the moment due to the ground on the footing itself. The same moment that we have calculated before and resulted in this steel reinforcement. This steel reinforcement is not due to a moment coming from the structure. No, it's the moment coming from the soil itself. This is the reaction of the soil inducing moment on the footing, and I'm putting reinforcement to carry it. So in my case, this column will not be here. It will be shifted a little bit this way. So when I shift it this way, in this case, this cantilever will not be small like this. It will be more. Then this amount of moment here will increase, so I have to increase the amount of reinforcement based on this. So this is what we said so far. This is the fixed case moment. It's an example of a column with a fixed direction for the moment, and this is the shape of the column after shifting it. What is the amount of shift? How many meters or how many centimeters? I just need a moment equal to the existing moment. If I add more moment, then I will. It's not a benefit. The big benefit is to just to get a moment equal to the existing moment, but opposite in direction. So how can I do this? Very simply, any normal force acting away from the CG induces a moment. What is the value of this moment? The value of the normal force multiplied by the arm of this, or the shift between the normal force and the CG of the footing. Okay? Then we can do the opposite. I know the moment that I want to reach, and I know the normal force of the column. If I divide moment by normal force, I will get the arm or the eccentricity. If I shift the column with this eccentricity in a direction opposite to the direction of the column, then I will have minus m. And I already have m, then in this case m minus m is 0. That's all. So this is the case where I have, in this case, the stress below the footing is just the stress due to normal force. If I have the column in the middle and I have a moment, suppose that this moment is not fixed direction. It can come from the right or from the left. In this case, I have to keep the column in the middle, but in this case, the stresses below the footing will be different. It will be variable. At one direction, it will be very small, and at one direction, it will be maximum. Why is it small? Can anybody tell me what is this minimum force? Or how can I calculate this minimum force and maximum force? Let me say it first. If this footing is subjected to two forces. Normal force, the stress of the normal force, you can say that it is something uniform, because normal force divided by area, it gives us a constant stress. Moment acting on an area it will induce compression in one side and tension on the other side. So, but the moment due to the column is always compression. So I have two cases. One side, I have the compression of the column plus the compression of the moment, and in the other side, I have the compression of the column with the tension of the moment. So this is F minimum is the compression of the column, the stress due to the compression of the column, minus the stress due to the tension of the moment. And here is the opposite, here is the summation of both. So, just thinking, this F minimum, in some cases it may be 0, in case both induce the same value. If the normal force and the moment, they both have the same value of stresses, so in one case, suppose it is 5. So I have 5 and minus 5, so the resultant will be 0. And in other cases, which this is the problem, I may have stresses due to moment that is more than the stresses due to the column. This is a problem. Suppose you have a column acting on a footing and it's giving a stress. And then you start acting on this footing with a moment. If you increase the value of the moment, you will reach a case, you will find that your footing is tilting. It starts to tilt. When the stress is due to the moment, the negative stress is due to the moment, is more than the stresses due to the normal force. You follow me? Imagine that you have, this is a footing, this is the footing, and I have a normal force in the middle of this footing. So the whole footing is inducing compression on the soil. If I start acting with a moment like this, and this moment is trying to overturn this footing, the moment with the effect of the normal force, it is just reducing the amount of the normal force in one direction. Here, in this direction, because I'm acting with a moment, so I'm trying, then I increase the moment, increase it. Every time I increase it a little bit. When my force or stress due to moment is equal to the stress due to normal force, then I'm at the brink. I will start to lift the footing. I will start. In this case, this value will be 0. At this time exactly, it will be 0. Then if I increase more, what will happen? The footing will be lifted from the ground. This is a problem. Why? Because if the footing is lifted from the ground, then my original calculation for the stresses due to normal force is wrong. Why? Because my original calculation for the normal force was the normal force divided by the area, by the full area. And now you tell me that part of the footing is lifted. Then it is a little bit complication and it needs recalculation. We'll see a figure for that at the end of the lecture to understand what I mean. But now it is an introduction that due to moment, if I have the column in the middle, then I will have F minimum and F maximum. F minimum will be, of course, less than F maximum. It may reach 0 and it may be negative. That's all for this time. We have here an example for the permanent moment. We said it last time, so we'll just go through it very quickly. It's similar to the previous example. I have a normal force, I have a bearing capacity for the soil, I have FCU and F yield for the steel and concrete, but I have additionally a value for a moment, and it is a fixed moment, it is permanent moment, it is always in the same direction. the first thing I will do, this is the column dimension, it is also given here. I will take these column dimensions. I will, as we said before, as a reminder, in Egypt here we have two codes, geotechnical code, RC code. The geotechnical code uses the working loads, the RC code uses the ultimate load. So in my solution or in my examples, I have always to use both codes, because designing the area of the footing uses the geotechnical code, and designing the depth of the footing and the amount of reinforcement I uses the RC code. Then I will have to have both values for the normal, for the loads. So I have to have working loads for P, which is the normal force, and I have to have also ultimate load also. To get the ultimate load, I multiply by 1.5. So P working for the column is given, it's 1900. 1900 by 1.5, I get the ultimate. The moment, I have the moment given, multiplied by 1.5, I get the ultimate moment also. Bearing capacity is given, FCU and F yield are given. So I just elaborated the moment and the normal force to be ultimate and working. Then, using the geotechnical code, I divide the working load by the allowable stress of the soil. I get the required area. So my required area here is 10.56. 10.56 is the length by the breadth of the footing. Then I will have now two equations. The first equation, length by breadth is equal to the area. This is one equation. This is the first one. The other one, the difference between the length and breadth, we said that it is better to have it equal to the dimensions of the column. Though here, if you look at this, I will have here a different, but at least the other direction, I can still have a cantilever that is within range. Anyway, we'll just use these two equations, get the required dimension for L and B for plain concrete and reinforced concrete. Also, as a reminder, we said that are we going to use the plain concrete structurally, or just something as a barrier to put it on the ground to work in a clean environment? We said that we need it to be a little bit thick, because I think it was given here, yes, TPC is 30, so it is more than 20. So by the I have to take it with me. Suppose you calculated and you did not take it into consideration. It's correct, but you paid money and you did not gain anything in return. So it's not wrong, but it is not economic, because Okay, so we'll continue. We now need to calculate the eccentricity. We said that I want to calculate the amount of shift I will do for this column, so that it would induce an opposite moment in the other direction. So this is the moment. This is the value of the moment that is already existing. I need minus 800. If I have 800, then I need minus 800. So suppose this is minus 800. I divided by the normal force, I get an eccentricity 0.42. So it means if I shift the column 0.42 meter in an opposite direction to the moment, then the resultant will be zero moment. This is a sum. So what will happen? This will be my these are the dimensions that I've got for L and B and for plain concrete and reinforced concrete, and I was supposed to have here the CG. I will now, because I have moment in this direction, the moment is coming from this direction to this direction. So if I put the column in the opposite direction, it will induce an opposite moment. I just shift 0.42 meter, and this is my new CG for the moment. If somebody here is very clever, suppose I have two moments. I have moment in this X direction, moment in Y direction. What should I do? Different values of moment. I have moment here, I have moment in this direction. Suppose it is X direction. Suppose you have another moment in the Y direction. Can you cancel it also?
I can cancel it.
Yes. Yeah, so I here made a shift of 0.42, and this is the CG of the column. If I take this CG down here, what I'm doing? I am doing another eccentricity in the opposite direction. So if here the original CG of the column was here, I shifted this CG this direction. So when I shifted it this direction, I induced a moment opposite to the X direction. So suppose I take it from here and go down, then it is double eccentricity. Direct eccentricity in the X and eccentricity in the Y. So if I give you two moments, the answer will be also the same. The difference will be in the location of the column. That's all. If I give you moment in X and moment in Y, you take the moment of X divided by the normal force of the column, get the eccentricity of X. Take the moment of Y divided by the normal force of the column, the same normal force, get the eccentricity of Y. So you have double eccentricity. From the original CG, use the first eccentricity horizontally, then use the second eccentricity vertically. You get the new CG that will induce two moments, one in the X direction and one in the Y direction. Suppose that you have, I need just a drawing for a square, a rectangle, any here. Suppose I take this column from this location and I put it here. When I put it here, it will have moment in this direction, which is equal to the normal force multiplied by this eccentricity. And I have another moment in the other direction, the perpendicular direction, which is also the normal force of this column multiplied by this direction. So I will have double moments. You follow me? So this as a summary, depending on your location or on the column's location on the footing, it may induce one moment in the X direction, suppose, or in the Y direction, or according to its location, it may induce two moments, one in the X direction, one in the Y direction in the same time. So in this case, this footing can be subjected originally to two moments, one in the X and one of the Y, and by doing eccentricity in X and Y directions, I can cancel both and I end up with a footing as if it has no moment, but the column is shifted in two directions. Or in one direction, it depends on my example. Once I reach this situation, I shifted the column, whether in one direction or in two directions, then I will continue a normal problem or a normal design problem, but with a shifted column. It means that the cantilever here is not equal to the cantilever there. So I should calculate, of course, the moment due to this cantilever and calculate the moment due to this cantilever, and which is equal to the moment of this cantilever. The other side is not important because it will have the same steel. It should have the same steel, but the moment of course will be less. So this is the governing moment here, and this are equal, and they both are the governing moment for the steel in the perpendicular direction. So I just calculate the moment here and the moment there, and based on the bigger one I will calculate the depth, and when I calculate the depth I add 7 centimeters the cover to get the T. I make my checks for punching and shear, and once I finish and they are okay, I proceed with the amount of steel and I put the steel. Here is the moment. Just a reminder, the moment I use which W, I need W actual. What is W actual? W actual in this case will be the force by the area, but which force? The ultimate force. Why? Because I'm calculating now the stresses that will give me the moment to get the steel. This is the RC code. So what I do is that I take 2850. Let's check what is 2850 in my example. This is 2850. It is the ultimate load of the column. So the ultimate load of the column, I take it divided by the area, I get the stress below based on this stress, which is below the footing, the soil stress below the footing, I will use it to calculate the moment, whatever moment in any direction, this moment or this moment. So for the first one, this is my bigger dimensions, or 1.445 meter. So here is this is 1.445 meter. Here's a calculation for this distance, and this is the other distance in the opposite in the perpendicular direction. So using both Z1 and Z2, I can calculate M1 and M2. So these are the two moments. Of course, the bigger one is the one that will govern me in calculating the depth of the footing. I will take this one and to calculate the depth. And when I calculate the depth and I check that it is safe, I can use the other moment just to get the amount of steel. I have a fixed depth and I have a moment. Then using both, I can calculate the amount of steel. Of course, I could have used the same steel for this, but this moment is nearly half half of this, so the amount of steel will be much reduced in the perpendicular direction. So based on this equation, I will get the D, add the 7 centimeters, conduct the check of shear, conduct the check for here it is safe, conduct the check for punching. This is the check for punching, and it was, I think it was safe also. Anyway, safe or not safe. If it is not safe, then we will add few centimeters or say 10 centimeters to the depth to increase the depth, and it will be safe. Then I will go to the moment. As we said, we have two moments, M1 and M2. M1 was the 400 and something, M2 is 200 and something. I will use this to get the main steel in the long direction, and this to get the steel in the perpendicular direction. I think this ends this example. So now I have what is just remaining. I have to draw to show you the drawing. I will just use the other drawing to find to know the difference. If my column is here, not there, what will be the difference? Of course, the amount of steel will be increased. It will not be 6,518. It will be more than that. So I will put now the new amount. In this direction, obviously it will be more or less, it will be the same, or it may be a little bit less. Anyway, whatever you will get, you will put. So we'll put the other steel in the other direction. The column will be shifted, and that's all. The difference is nothing. The difference between the two examples is nothing. We just shift the column and continue the problem. The only difference will be in the length of this cantilever. In this example, this cantilever was the same as this, as this, as this, so we only designed one section. But when I shift this, I will have two sections. One for the bigger cantilever and one for the cantilever in the perpendicular direction. That's all. So it is a very trivial example, and the difference is nothing. So up till this level, the amount of calculation is minimum, and we can still calculate a footing subjected to a moment very easy without any problem. What you are going to see now is how we can really face problems when we calculate something with a variable moment. Variable moment is a problem. I want to show you there was a drawing here that I wanted to. I think we said all of this. This was the checks, and then we got the moment. Yes, yes. Starting from here. Just a moment, I will tell you. So we can stop here. And the next part of the lecture will take the temporary moment where we have the moment with a variable direction.